So my talk will be very short. I put myself at the end because I wanted to bring some things. I didn't want to talk so much about my own research, but to bring some thoughts that I've been thinking about aging. Oh, sorry. Lately. Again, related to. So I did for a number of years. I worked on. Okay. For a number of years, I worked on telomeres, and the more I understood about telomeres, the less I was convinced that they have anything to do with aging. And our last meeting actually was very heavily on aging and that, on telomeres and related to aging, and I completely convinced myself that they have nothing to do with aging.
So the meeting was a success.
The meeting was complete success in my mind, but disappointing, I guess, for the rest of the people. So I in fact, decided cancer is much better field to work on. But recently, in the past 2 years, with colleagues at Yale University, we were able to, and they did all the experiments, I did the theory, but we were able to actually observe the dynamics of hair follicles, normal hair follicles, the stem cell compartment in living mouse. So this is a transgenic mouse which expresses fluorescent protein, and then using two-photon microscopy, you can actually observe the dynamics of the hair follicles. And contrary to belief that, in fact, these stem cells are dead, the hair follicle stem cells are not dead. The hair follicle is retracted in people that don't have hair, and then somehow the signal for regrowth doesn't come. As Arnie mentioned in the beginning, it's about 28 days that the hair follicles contracts and then expands, contracts, expands, but the stem cells never die actually. Only the progenitors die, and then the stem cells again repopulate the hair follicle. So there is hope in that sense. So the phenotype, the aging phenotype, which is losing hair, in fact here is dysregulated at the tissue level. So it is not the individual cell, but the signal that makes those cells grow is dysregulated. So I just wanted to bring this not so much to advertise this research, but just to say that the phenotypes that we observe as aging could be coming from very, very different physical and chemical phenomena. And it's not necessarily related to each other. The graying of the hair is a very different phenomena from losing hair, although we both identify culturally as a aging phenotype. But reading actually Chris's papers, and I went back and started from 1999 and followed the logic of these papers in looking at small system far from equilibrium. It occurred to me after reading some papers on stem cell, programmable stem cells and reprogramming those stem cells, and talking to Arnie, who gave me all the examples that actually he talked today. It occurred to me that perhaps what's happening is that through wear and tear of the molecular parts in a cell, just due to these irreversible thermodynamic processes that are happening far from equilibrium, that perhaps this actually is the normal aging processes related to this wear and tear because the organism has to live far from equilibrium. Supposedly we can make a human that lives very close or at equilibrium, and that human's going to live extremely slowly and wouldn't do anything. So in order for humans to be useful species, they need to operate, and cells have to operate far from equilibrium. And the question is, so I'm going to have more questions than actually answers, but to me I'm going to show only one formula. But this is a formula that actually was derived by Jeremy England a few years ago, and then it was clarified by David Ruel actually very recently in a preprint. And basically this is an equality that says that if you have two states which are equilibrium states, exactly as in Chris's thinking and experiments, both are equilibrium, and then you connect these two equilibrium states through a non-equilibrium path, then the probability of going from state 1 to 2, the conditional probability that you are initially at time 0 at state 1, and then you go to state 2 at, over time t, divided by the conditional probability for going back, the more irreversible the process is, the higher the entropy that you have to release in the environment. And so, given that delta Q is the same. But so in some sense, the question is, when you have all these non-equilibrium processes driven by ATP, and we suspect that only about 60% of the ATP energy is used actually for useful chemical reactions. The rest is released as heat or as heat in the, let's say, surrounding water, or it's taken by structural changes in the surrounding molecules, or by vibrational modes in the surrounding molecules. Some degrees of physical degrees of freedom have to relax that energy. So the question is it feasible or possible that in fact this non-equilibrium process lead to structural changes in the molecules in the cells, and eventually these changes lead to something that doesn't allow the tissue to rejuvenate. And so just to give you some numbers, for example, one process like this is transcription. So genes are being transcribed by RNA polymerase. The polymerase have to open the DNA. The structure of the chromatin has to open in order for this polymerase to be able to transcribe. And if you look at the energies, the local energy that is being released is about 4,000 degrees Celsius. So the number of errors is about 1 per 10 to the 4th nucleotides read, and the speed is about 17 nanometers per second. So there is a competition during transcription, for example, that was actually described a long time ago by Charlie Bennett, that the speed, the error rate, and how far from equilibrium you are related. We could do very, very slow transcription, which is very close to equilibrium, but there will be a lot of errors because detailed balance will tell us that the probability for going in one direction is equal to going in the opposite direction. So we don't want detailed balance. We want actually to be able to read in one direction faster. Now, another molecule that actually could be doing something that is related to this idea is the nucleosome. So the nucleosome is a complicated structure made of approximately 146 base pairs wrapped around proteins. And that structure breathes, so it opens and closes, and the cycle is about 300 milliseconds. So I did a calculation a few seconds ago because I heard Jeffrey West's idea that engines survive about 10 to the 8 cycles. And this, over 100 years, in one cell, this nucleosome will breathe 10 to the 9 times. So perhaps this is also related to the fact that the nucleosome actually, we know in aging, changes structurally. We do know that chromatin, the bigger structure made of nucleosomes, also changes structurally. So there are a lot of structural changes that appear in these molecules as the organism ages. So the question is it because it's just operating into these cycles of transcription and translation? Is it something that just the normal cycle in the cell brings structural changes in the molecules that eventually show up as dysfunctional molecules and lead to cells that actually senesce or die? And then I discovered this methylation phenomena. I knew actually about that paper with the 322, I think, CPG sites. And it's amazing because you would ask, why does it take 100 years for the DNA to get methylated? The methyl group is extremely small. It's just a carbon and 3 hydrogen atoms. The DNA should be available for methylation right away, just at conception, basically. Why does it take 100 years to methylate? And it's interesting that the nucleosome, actually, the actual nucleosome structure is protective for methylation. If the cell is in a condensed phase, then the methylation is very little. So the DNA, the nucleosome has to open for the methyl group to be able to methylate the DNA. And so perhaps what happens is that over time, as the structural changes in these nucleosomes happen, more and more methylation happens, and it's just a continuous process that at the end of the day, after 50 or 65 years, as Arnie would say, the DNA is methylated in such a way that these cells cannot reprogram their transcriptomes anymore. If the cells can't execute programs of differentiation and which is rich enough to maintain the tissue or the organ function, these cells are useless for the organ, and then the organ will fail. So the question is this related, actually? This methylation pattern that's been observed and gives, I think the Pearson coefficient was like 0.9995 with the age, whether it's actually coming from the natural physical process. It's interesting that your advisor told me that the promoter sites get methylated, and the internal part of the DNA of the genes actually get demethylated with age. So perhaps the structural changes are such that promoters are, in fact, promoters are located on the DNA in different places on the nucleosome than actually the internal parts of the gene. So these are only thoughts that I really real fast one. This is a paper that shows that with age the methylation patterns change, but we have much better now results, of course. And so one would look at other, perhaps other molecules that could be. There are several diseases that are related to premature aging. For example, the Werner syndrome or the Bloom syndrome. They have defects in DNA helicases. Everything goes wrong with this. The telomeres, the DNA repair, everything goes wrong in these syndromes. But these are again phenotypes, human phenotypes. Whether that's really related to real aging is not clear. But again, I think looking for molecules and where these structural changes can be happening as the cell cycles, I think is very important. It might be very reductionist in thinking, but again, I think that it's important to understand what happens with the energy when it's released. As Jeffrey said, there are these nodes that take the energy, and perhaps we can actually find out where those nodes are. And of course, the calculations are complicated. One has to do quantum chemical calculations to see, for example, in particular chemical reaction where the energy goes. But perhaps it's a good thing to know. And so, just last point, came a question here: why life doesn't age for 4 billion years? I think that we need to really distinguish aging of an organism which is made of organs that have specific function, and changes in genomes and methylation patterns in bacteria, for example, in single-cell organisms. If a cell doesn't die, if a bacteria doesn't die due to certain changes in the methylation pattern or in the genetic structure, that bacteria is viable as long as it divides. So there is no aging there. So the bacteria is either a new phenotype, which survives, or it's dead, which is not true for an organism made of organs. So in that sense, this phenomenon probably also persists in bacteria, that the DNA changes and all the molecules changes, but those that survive and continue as new phenotype or new species, and the rest are dead. And so I just want to acknowledge some people that I have brought these ideas to, and I have had some very nice conversations. Thank you very much.
Are we asking questions or breaking for dinner?
We have a few minutes.
5:32 now.
So we have 5 minutes,
yeah,
maybe 5
well,
minutes.
it hurts, so,
Go easy, Bob.
Oh, don't worry.
Ruslan, there are a lot of ideas floating around, and let's say, at the end of the day, there's one that surfaces again and again, which is the chief epigenetic memory mechanism of life is methylation. And I myself have no way to judge whether that's true or not. It's just something you can measure. Now, holding that thought, you're talking about energy flow. There is a very fundamental principle of machinery that isn't equilibrium thermodynamics. It's a principle of machinery, that you have to make entropy to make a decision. In other words, decision-making is inherently irreversible. Okay? You've got two options, you have two choices, two paths to go, and you choose one of them. And the act of choosing means you can't ever go back. And that act of choosing and not ever being is the generation of entropy, which closes the door behind you. Now, we make computers based on this principle today because it's a very, very powerful way of designing decision-making machinery that's very big. people are always dreaming about reversible computers, but those computers can't make decisions. So that means they can't do many of the elementary things that computers do today. So the point I'm trying to make is that the dissipation of energy that we're talking about is not just some accident, okay? If you're strategizing and trying to solve problems, you're an organism trying to solve problems, it's as a physical principle, you have to generate a certain amount of entropy per decision. And the more decisions you're making, like running away from dinosaurs or whatever, the more energy you have to burn. And yes, that process is doing, you know, it's an engine, just like a transistor is an engine, and it's having collateral damage. So this idea, I think of the process of decision making damage necessarily as a collateral effect is highly reasonable.
Yeah, I completely agree with you. And again, I think that again to bring back Chris's talk. So when a nucleosome opens in a high non-equilibrium state, we might expect that it closes in a different state. It might actually trace a different path. It might actually not close into the identical nucleosome that you started with, which of course would be the same if you went through an equilibrium state, which is reversible. So you just reverse it and you get back to the original. But that would be totally useless. I think that exactly partly because of that. So, but these are all speculations, but I think that it could connect somehow the thermodynamics with the tissue reprogrammability of these stem cells and their lack of or diminished repertoire as age goes on. Because I think that at the level of organism, we need to agree that the aging is to a large extent at the tissue level, that is at the population of cells in an organ that have to do a function.
Any other questions?